Thank you very much, and it's a pleasure to be back here to talk to the BADAS team. So, yes, hopefully that says it all. Beginning of everything, a brief description of the origin and the very early history of the universe. Let's start with what the universe actually looks like rather than what it should look like. This might look like a simulation, but actually it's a 3D atlas. It's lots of galaxies, positions in the sky have been plotted out, the distances have been measured, and a computer has then generated this 3D atlas, and then we have a little fly-through. So although it looks like a bit of simulation, it's a genuine, this is what the universe looks like, at least in our neighborhood. In other words, a fraction of a billion galaxies around where we currently reside. And the galaxies aren't uniformly spread, they are bunched together. We see clusters, we see superclusters. Every once in a while, you'll notice that there are regions of the sky which appear to be voids. There's a very few galaxies in a given volume, and other areas where there appear to be filaments, long lines of clusters of galaxies. So if we want to be able to explain the way the universe is, we have to be able to get something which looks close to the actual distribution that we see, the actual observed universe. So we know we can take static images like this and we see lots of stuff. There's definitely lots of stuff out there. Lots of stars, but this is mainly talking about the large-scale structures of the universe. Clearly, there are lots of galaxies, something like 1 trillion galaxies or so in the observable universe. There's a lot of stuff out there that we can see in the observable universe. Who knows what's going on outside the observable universe, so that's not going to be what we're discussing here. We see a lot of stuff in the observable universe. Where did it all come from? That's the question we're trying to answer. So I'm talking about the creation of the universe. When did this happen? As far as we know, about 13.8 billion years ago. How long did it take to make a universe? It takes about 3 minutes to make a universe, or at least ours apparently was made in about 3 minutes. Where did it happen? That's sometimes a question. Where was the Big Bang? Well, the Big Bang was everywhere, because it's the creation of everything. And why did it evolve the way it did from this start 13.8 billion years ago to the present day? Well, it evolved the way it did because of the laws of physics. And how do we know all this? Same answer, because of the laws of physics. So, a few comments before we get stuck in. Nature is not repetitive. In other words, when we observe the universe, we find that things don't always happen again and again and again exactly the same way. It might have felt like that during lockdown, but generally speaking, nature is not repetitive. Otherwise, life would be really, really boring. Also, nature is not unpredictable. So it may not repeat, but it's not so unpredictable that we can't possibly make sense of what's going to happen next. We can still make some predictions based on what we've seen in the past. So it's not repetitive and it's not unpredictable, hence it's really interesting. But the question is, why is the universe the way it is? What are the rules of the game, if you want to think of it that way? If we were dealing with chess, assume you didn't know what the game of chess was. Could you work out what the rules of chess were by looking at a picture like that? The answer, I think, is no. Simply by looking at various odd pieces at various odd positions on a board cannot tell you what the rules of chess are. In much the same way, you can't look at a galaxy and figure out how did that galaxy come to be, simply by looking at a picture of it. With chess, you might have a chance of understanding the game if instead of a picture you had a movie and you watched two people play chess. Then you would get an idea of how the pieces move and what the rules are that allow you to move particular pieces on the board. We can't really do that with galaxies in the sense that we can't watch them evolve. If we were to stare at that galaxy and wait until it changed, we would have to wait for hundreds of millions of years simply for it to rotate and for many billions of years for it to change. So we haven't got the luxury of a movie that shows us how the universe evolves. The best we can hope to do is to take a snapshot of lots of galaxies at different phases of their evolution. A bit like, instead of watching a chess game evolve by watching a movie, take a snapshot of 1 million chess games all at random positions within the game, and that will give you an idea of how to construct the rules that dictate how chess evolves. So when we look at a picture like that, if we do a deep field, a long exposure, we're looking at galaxies, some of which are close, some of which are very distant, and hence, because of the finite speed of light, we're looking in some sense back into the past. So we can get an idea of what galaxies look like now and what they used to look like billions of years ago. So we can get an idea by looking at images such as deep field, not just one, but hopefully many such images. But when we look into the universe, it looks rather complicated. How on earth can we dictate how that came to be? How can we set up, or how can we understand the rules that allow a structure like that to come into being? Perhaps some of you recognize it's a very small part of the constellation of Orion, as indicated by the Horsehead Nebula down in the bottom left there. Surely something so complicated must have a very complex set of rules that allow something like that to exist. Well, by comparison, we can say, well, what about a mathematical set of rules? Here, there's a mathematical collection of pixels, effectively colored pixels in a two-dimensional plane, colored according to a mathematical formula. And if we zoom in, we find that this structure, this so-called Mandelbrot set, it's called a fractal. If we zoom in, we see more and more detail. In much the same way that if we zoom into the Milky Way, we see more detail of stars. If we zoom into a solar system, we see more detail, planets. If we zoom into the planet, we see detail, us. If we zoom into us, we see more detail, cells. If we zoom in, we see, etc., etc. It's the same for the Mandelbrot set. It's not just a million pixels, or whatever it is we're looking at on the screen here. It is, in principle, an infinite set of pixels, and the more we zoom in, the more detail we see. The more we zoom in, it does not repeat, in much the same way that one star might look superficially similar to another, but they're not the same. The detail is different. And this particular collection of pixels on the screen never repeats, no matter how much we zoom in. So, if this is an incredibly complex, you could argue infinitely complex collection of colored pixels, what formula was used to generate the entirety of the Mandelbrot set? Not just the few pixels we're looking at here, but what about the trillions upon trillions upon trillions of pixels which aren't in this picture? The formula that generated that pattern is that. Z equals Z squared plus C. We don't have to worry about what the Z means. The point is, it's a very simple formula, but it generates an extremely complex, arguably infinitely complex pattern. So just because the universe looks very complicated does not mean the rules of the game are beyond our comprehension. And one of my favorite quotes from Einstein was this one, in which he says the most incomprehensible thing about the world, treat that as universe if you wish, the most incomprehensible thing about the universe is that it is comprehensible. Even though there's no particular reason why we should be capable of understanding how the universe works, it would appear that we can make sense of it. We can observe, we can develop theories and hypotheses, and we can comprehend how the universe is put together. There's no reason why that should be the case, but it appears that this particular ape that came down out of the trees 1 million years ago is capable of understanding how the universe is put together. So just because it's complex does not mean it's incomprehensible. So the flow of thought that helps us understand how the universe came to be is something like this. An observation which we've known about for 100 or so years now, the observation that galaxies are moving away from each other. The universe is expanding. So another set of observations we can make, apart from the astronomical one, is to try and understand how the world is put together by doing experiments in the lab here on Earth. And for instance, experiments such as particle physics experiments, banging things together, seeing what happens, atom smashers if you wish. The Large Hadron Collider is trying to understand what atoms are made of and what those subatomic particles are made of to try and understand how the universe is put together. So on the large scale, we can look at the universe. On the small scale, we can do particle physics experiments, which helps us understand the nature of matter. But we do have to make some assumptions. Physicists think they know everything, but they do have to admit that there are some assumptions in here. And one of the assumptions is that the laws of physics at one point are the same as the laws of physics somewhere else. If the laws of physics for you sitting there were not the same as the laws of physics for me standing here 5 meters away, then we would have no ability to make any sort of sense of the world. If the laws of physics changed from one point to another, if the laws of physics here were not the same as the laws of physics in Australia, we would be totally and utterly stumped. We would not be able to make sense of anything. And by inference, we assume that the laws of physics in Alpha Centauri must be the same, and the laws of physics in the Andromeda galaxy, and the laws of physics essentially everywhere. The other one is that the laws of physics are immutable in time as well as space. In other words, the laws of physics don't change. If we're trying to understand the world and the laws of physics yesterday were not the same as the laws of physics today, again, we would have no chance whatsoever of understanding anything. If the laws of physics tomorrow are all different, then all bets are off. We cannot make predictions about how things are likely to turn out. We don't, it's an assumption. That's why it says assumption, because we have to assume that they're immutable. If that's not true, we have no chance of understanding anything, ever. So we have to assume that the laws of physics we're talking about are immutable, because otherwise we cannot make any progress. So it's an assumption. If we take the observations and that assumption, we come to the conclusion that the universe was created 13.8 billion years ago in a very hot, dense state, and has been expanding and cooling ever since. So the big question is, when we look into the universe, we see an awful lot of stuff. Where did all the matter that we see in the observable universe come from? That's the question I'm trying to answer. And coming back to this same question of, we assume that the laws of physics don't change with time, so we can ask the question, how far back in time can we go to the Big Bang 13.8 billion years ago before we have to say, well, we don't really know whether the laws of physics actually hold up or not? What about the first 1 billion years of the 13.8 billion year history of the universe? No problem at all going back 12.8 billion years. Can we go back to the first 1 million years out of the 13.8 billion? Yep, no problem at all. Laws of physics definitely hold up to that point. What if we go back to the first 1,000 years? Yep, first year. Yep, first day. Yep, first hour. Yep, first minute. Yes, first second. Yes. Can we go back further in time, further than the first second? Can we go back to the first millisecond after the Big Bang and say we honestly believe the rules of physics then were the same as the rules of physics now? Yep. What about the first microsecond? Yep. What about the first nanosecond? Probably. What about the first picosecond? Not too sure. We cannot make any claim about our understanding before the first picosecond, the first trillionth of a second after the Big Bang. Before the first picosecond, we are on shaky ground. We cannot make any experimental observations which back up our claim that we might understand what's going on at that point. Everything after 1 picosecond, everything from 1 picosecond up to the present day, we are on fairly solid ground. Mainly because we can verify in lab experiments any hypothesis we want to make from 1 picosecond upwards. We can't 1 picosecond downwards. I'll explain that threshold in just a moment. So that was a very long introduction to what it is I'm trying to talk about. Looking at the universe, trying to make sense of it, and from the observations and our understanding and our assumptions about the laws of physics, let's see if we can understand how the universe came to be. So I've got one slide with a few basic ideas before we launch into what happened in the first fraction of a second, what happened in the first few seconds, what happened in the first few minutes. It'll take me about half an hour to cover the first few minutes, and I can't keep that up for the entire 13.8 billion year history, so I'll have to change gears and then fast forward to 377,000 years after the Big Bang. There's a particular reason for that number. And then I'll fast forward again up to the present day, 13.8 billion years later. So it's a very non-linear way of traveling through time from zero up to the present day.
The only thing that makes me a bit puzzled about it is, did you see that program about Cassini, whatever it was, going to Saturn? On the rings there were these mountains, but they were upside down.
Beg your pardon? What were they?
They were mountains, which were upside down.
I haven't seen upside down mountains, no.
Well, that's what they're saying on the
Yep.
telephone.
Yep. In
a Saturn ring.
in the ring.
Yeah.
So by mountain you mean what?
Like a mountain with a peak.
Well, the rings aren't solid, so the definition of a mountain doesn't really work when you've just got a lot of particles floating around. So I don't know if that means... does that mean the rings... does that mean a protuberance? Does that mean some particles out of the ring plane, perhaps, is what they mean? But, well, they certainly change the position of the various particles. But given that there's no up or down, in the sense of a mountain implies something is poking up, but for the rings, they can either be one side or the other side. So I don't quite know the difference between a mountain and a valley in that context. So maybe I'll go look it up. So the basic ideas that we need are some of the concepts I'm sure you're familiar with. So we are made of atoms. Atoms comprise a positively charged nucleus and negatively charged electrons buzzing around them. So, given enough energy, we can take an atom and rip it apart into its constituent parts, a nucleus and electrons. To the best of our knowledge, electrons are fundamental. We can't take an electron, cut it in half, and look at what's inside. In other words, it is just a particle. It's not made of anything else. Whereas a nucleus is made of other stuff. Given enough energy, we can take a nucleus, rip it apart, and find that it's made of protons and neutrons. These, unlike an electron, are also made of other things. We can take a proton and look inside. We can take a neutron and look inside. Given enough energy, we can start to look inside these, and we find that protons and neutrons are made of particles. We don't have to worry about the silly names, but they're made of particles called quarks. As far as we know, quarks, again, like electrons, can't be cut in half to reveal inner structure. We may be wrong with that, but so far we failed to find any inner structure in quarks. So in terms of what is the world made of, it appears to be made of quarks and electrons, because quarks plus electrons make atoms, atoms make molecules, molecules make us, and everything else we see around us. So notice that each of these steps in this sort of Russian doll model needs more energy. If we want to break a molecule into atoms, that's relatively easy. Breaking an atom into nuclei and electrons takes more energy. More energy is required to break a nucleus. More energy is required to break a proton. So there's an implicit energy scale here when we think about this Russian doll model of how the world is put together. There's low energy at the top, and it requires more and more energy as we go down. But to a physicist, low energy and high energy are pretty much the same as low temperature and high temperature, because temperature really just means how much energy does each particle have. So when we say low energy and high energy, we really mean cold at the top and hot at the bottom. But remember, we've just surmised that the universe was born hot and is cooling down. So there's also an implicit time arrow here, in the sense that we believe the universe was built from the bottom up. You can't have atoms in the early universe when the universe is really hot, because if it's really hot, an atom can't stay together. There's so much energy, every atom is going to be ripped apart. If you try and make an atom, it will instantly fall apart. Similarly, you can't have nuclei and you can't have protons when the universe is too hot. But at some point, if we wait long enough, it'll be cold enough for quarks to get together and make protons. Before that point, the universe was too hot. If you wait a little longer, the universe will be cold enough for protons and neutrons to actually make nuclei. If you wait longer, it'll be possible for a nucleus plus electrons to make atoms. So this is the process, and this is the timeline from the bottom up, and that's what I'm going to describe. But we have to get rid of the elephant in the room first, and the elephant in the room is what happened at t equals 0, what happened at the instant of t equals 0 when the Big Bang occurred. And the answer, of course, is we don't know. Science cannot provide a definitive answer. I've already said that we're on shaky ground before the first picosecond, and this is t equals 0. You may think 1/trillionth of a second is near as damn it 0, but no, not to a physicist. 0 and 1 picosecond later are two very different things. We really don't know what happened at t equals 0. According to the weird world of quantum mechanics, it's possible that there was a fluctuation, a so-called quantum fluctuation, in which you can get something from nothing. That's perfectly okay. It sounds like a cheat, but quantum mechanics tells us that you can get something out of nothing. It pretty much happens all the time. So you can borrow energy and matter, because they're almost the same thing as far as E equals mc squared is concerned. You can basically borrow energy from nothing and make a universe. I know it sounds weird, but quantum mechanics is weird, and that's a completely different talk.
Where does it come from then?
Something from nothing comes from nothing.
How?
You can get something from nothing. That's part of what quantum mechanics tells us. You can get something from nothing.
How?
There is no problem with getting something from nothing, because that's how quantum mechanics works. You can borrow as much energy as you like as long as you pay it back. Energy times time has an upper limit. In quantum mechanics, you might say you can't get something from nothing. Well, quantum mechanics allows you to do that as long as that product, the amount you borrow multiplied by the time, is paid back quickly enough.
So you have energy then, to get something from nothing?
No, you take the energy from nothing. Yeah, it just happens. You can get energy from nothing as long as energy times time has an upper limit. So there's a fundamental principle called the Heisenberg uncertainty principle that says you can do that as long as energy times time isn't arbitrarily large. In other words, you can borrow a lot of energy for a short time, and that's fine. You borrow energy from nothing, and you pay it back a little bit later. The universe doesn't notice that that's happened. In much the same way, you can take money from a bank, and as long as you pay the interest, the bank doesn't worry about that. If you borrow a lot of money, you have to pay it back either very quickly, or you get a huge amount of interest building up, which you then have to pay back. So the question is, if you have an upper limit of energy times time, and you have, therefore, you can borrow any amount of energy you like as long as you pay it back within a certain time frame. We know that happens because we can measure it in the quantum mechanical sense in laboratory experiments. But it is supposed, it is hypothesized, it is thought by many people the total energy of the universe might actually be zero. So if you're allowed to borrow energy as long as you pay it back, according to the upper limit of energy times time has an upper limit, if the total energy of the universe is actually zero, then there's really no problem borrowing zero. In a sense, you're borrowing nothing. The total energy of the universe might be zero, because if you look at all of the positive energy that's built into matter and all of the negative energy that's built into gravitation, some people surmise, we haven't got an accurate figure, but some people surmise that the total is actually zero. And that might explain why we're allowed to borrow the energy, because the total energy we're borrowing is actually nothing. So that almost certainly sounds like a total and utter fix. And I refer back to the second line, we do not have the answer. That is a hypothesis that the total energy is zero, therefore we're allowed to do this. And I refer you to the third line because it does sound weird, but yes, the world is weird. Quantum mechanics is really weird. We've been living with quantum mechanics for 100 years now, and we've been trying to prove quantum mechanics is wrong. After 100 years, we still cannot prove that quantum mechanics is wrong, even though it gives really weird results, like you can borrow energy from nothing as long as you pay it back quickly. So, t equals 0, we do not know. That is simply a hypothesis. We now fast forward to a time frame of that many seconds. In other words, 10 to the minus 35 seconds. The universe, by which I mean the observable universe, is the size of a golf ball. In other words, the observable universe, which is currently about 100 billion light years in diameter, used to be a lot smaller. Used to be about that volume, roughly the size of a golf ball. Trying to imagine everything in the observable universe being inside that golf ball takes a little bit of doing, I admit, yes. But it is thought that that is what the early universe looked like. A, small, and B, dimpled. That's why I choose a golf ball rather than a beach ball or anything else. The early universe had small fluctuations in density and temperature. So that's represented, it's an analogy, it's not strictly on the surface like a golf ball is, but you can imagine that there are variations in density. Eventually, when the golf ball has expanded to a much, much, much larger structure, these small variations in density will give rise to all the structures, i.e. the galaxies, the superclusters, etc., that we see today. Now we come to the point where we're on solid ground. We're going to fast forward to 1 picosecond, 1/1,000,000,000 of a second after the Big Bang. The universe has expanded from the size of a golf ball up to something about the size of the solar system. Yes, the solar system doesn't exist yet, but just to give you an idea of scale. In other words, it is now a few light hours in size. It only took a tiny fraction of a second to go from a golf ball up to a few light hours in diameter. So clearly it's expanded by substantially more than the speed of light, which is perfectly okay. It's not breaking any rules. The temperature has now fallen to a balmy 10 to the power 15 Kelvin. And the reason that this picosecond is the watershed, i.e. we think we understand from this point onwards, is because the energy that each of the particles in the universe, this soup of particles, which I sometimes call the quark soup, it's actually a soup of all particles, quarks and electrons and muons and other things, but quark soup just sounds catchier. Basically, the soup of all the particles that could be generated and were generated at the time, each of the particles at a temperature of 10 to the 15 Kelvin has the same energy as the energy of the protons zooming around in the LHC, the Large Hadron Collider. In other words, we can actually test ideas because the energies involved are the sort of energies that we can reproduce in the LHC. So prior to this, the energies were too high and we can't reproduce them in a particle accelerator. But from this point onwards, we can reproduce the energies in a particle accelerator, and therefore if somebody has a theory or a hypothesis that says maybe this happened, maybe that happened, then it can be tested by doing these sorts of experiments. And hence, from a picosecond onwards, we think we've got a reasonably good idea of how the universe evolved. T equals 0, we don't know. Golf ball is a hypothesis. Picosecond onwards, we're cooking on gas. We know what's going on. Matter and antimatter are continually being made because energy and matter are continually exchanging backward and forth. If we've got a certain amount of energy, we can make matter and antimatter. Antimatter is just the mirror image of matter. For instance, an electron, which is a negatively charged particle, will have a duplicate, which is the same except that it's positively charged. We call it an anti-electron. Similarly, every quark will have an anti-quark. A muon will have an anti-muon, etc. As far as we can tell, it looks like a rule of the universe that every particle has an equivalent antiparticle. We're made of the matter equivalent of protons and neutrons and electrons. The antimatter doesn't seem to be around at the moment for a reason I'm about to explain. So energy and matter are continually exchanging backwards and forwards, and when I say matter, actually it's equal amounts of matter and antimatter. Originally, we believe that they were made in exactly equal amounts. In other words, a certain amount of energy. I don't know how to draw energy, so I'm just drawing energy as a capital E rather than try and find some particular icon for it. So a certain amount of energy can generate matter and antimatter. It's probably not going to be an orange and an anti-orange. It's probably going to be a quark and an anti-quark, or an electron and an anti-electron, or a muon and an anti-muon, or something. But the point is, it doesn't actually matter. Energy makes some matter and its mirror image in antimatter. They almost immediately annihilate and generate more energy. And we're back to square one. The energy can then make some amount of matter and antimatter. Probably not hot dogs, I admit, but it will make something and its anti-equivalent. And they will annihilate and go back to energy. Energy to matter and antimatter, back to energy. Back and forth, back and forth. This will be continuing back and forth very rapidly in the early universe. Somehow, through a mechanism that we really don't understand, somehow that balance was disturbed. Instead of always making the same amount of matter and antimatter, for some reason or another, one gained an excess over the other. In other words, we had a certain amount of matter being made and a slightly different amount of antimatter in the early universe at about this time of order picoseconds. I've shown it as an excess of, 10% or something. It wasn't quite that large. The excess of matter over antimatter was not 1 part in 10, it was tiny. It was 1 part in a billion or so, but I'm not going to draw a billion oranges on the screen there. So if we have a slightly different amount of matter and antimatter, when the two annihilate, the first pair will annihilate to produce energy, the second pair will annihilate to produce energy, etc. We end up with a whole load of energy. At the moment, we're talking about energy in the form of electromagnetic radiation, but we have a little bit of matter left over because it hasn't got a partner to annihilate with. So the universe is actually full of the result, and that means the universe is full of light and matter. We are simply the leftover bit. So we can be thankful that there was an imbalance between the two, because that imbalance is what resulted in us. If there wasn't that imbalance, the universe would simply be full of photons and nothing else. There would be no stars, there would be no planets, there would be no cricket, there would be no cats. It would just be full of photons. So,
there's a reduction in energy associated with
1 part in a billion, tiny amount, yes, that's right. And it also tells us that there are not 9 photons for every particle, because I said that that's actually 1 in a billion. There's actually 1 billion photons for every particle. If we add up every particle in the universe and every photon in the universe, the number of photons outnumber the number of particles by approximately 1 billion to 1, because that's where the asymmetry comes in.
So if that's going all the way through the universe,
Yep.
that means there's people like us then.
People like us?
Yeah, well, got to be in there. Because it's done to us. It's involved us, doesn't it? Is what you're saying.
That has made us, yes.
Yeah. But if the laws of physics are uniform throughout the universe, it's going to make it elsewhere, isn't it?
The idea that life exists everywhere is very contentious. The fact that life exists here does not mean necessarily there's life in Alpha Centauri and whatever.
Okay.
In other words,
The laws of physics would say that, shouldn't it?
the laws of physics are the same, but the chances of life evolving, we don't know what those are. We don't know whether that's 10% or 1 in 100 or 1 in a million or 1 in a billion or 1 in a trillion. So I think certainly there is life out there. It's very difficult to predict how much, because we don't know what the probability of life evolving is. Just because it happened here doesn't mean it's inevitable. It doesn't seem to have happened elsewhere as far as we know, but the absence of evidence is not evidence of absence. So regarding life elsewhere in the universe, we do not yet know whether or not it's common.
It would be like that, would it?
Well, it would come from the same particles that were left over after the 10 to the 9 photons had done their job. So we're now fast forwarding from picoseconds to milliseconds. So it's still less than the snap of a finger after the Big Bang. Matter and antimatter are continuing to pop into and out of existence. Energy to matter and antimatter, back to energy, etc., backwards and forwards, backwards and forwards. Now that the universe has cooled off a little bit, because we're a millisecond after the Big Bang, then it's possible for the quarks to make protons and neutrons. I am not going to turn this into a particle physics lecture. I'm not going to explain why some of these are red, green, and blue. I'm not going to explain why some quarks are labeled U and some quarks are labeled D. All that we really care about is there's lots of quarks in the soup. Every so often, 3 quarks will get together. That doesn't work too well, does it? On the left-hand side, when 3 quarks get together in a particular way, that particular bag of quarks is what we call a proton. And a slightly different bag of quarks is what we call a neutron. A proton and a neutron are just labels for a bag of 3 quarks that happen to have this particular set of characteristics. We don't need to worry about the details. But there's so much energy sloshing around in the system because the universe is still very hot, then basically protons turn into neutrons and neutrons turn into protons, because the idea of 3 quarks in a bag, the idea is rather fluid. In other words, the quarks will keep changing, the matter of quarks will keep changing into energy, which comes back into matter again and doesn't necessarily make the same quarks. So a bag of 3 quarks will continuously change from protons to neutrons, backwards and forwards, backwards and forwards. What happens when we get to 1 second? The universe has cooled a little bit further. The universe is now only 1 billion Kelvin. That might still sound ridiculously hot, but bear in mind that's the sort of temperature in the middle of a hot star. So we're not talking about ludicrous temperatures anymore. We're talking about the sort of temperatures that we can sort of understand in the universe today. But after 1 second, at only 1 billion Kelvin, it's now too cold for protons and neutrons to readily swap backwards and forwards. Remember the Russian doll model? As the universe cools, it can no longer provide enough energy to, for instance, rip protons apart or rip neutrons apart. So after 1 second, the universe has made lots of protons and lots of neutrons. Protons are a little bit lighter than neutrons by approximately 1 part in 1,000, about 0.1%. How do we know that? We're coming back to the assumption, if we can measure it in the lab, we assume that that was true in the early universe. When we measure in the lab, we find that protons, which are red in this schematic, and neutrons, which are blue, protons are a little bit lighter by 1 part in 1,000. And if it's true now, we assume it was true then. If that wasn't the case, we can't possibly understand anything about the universe. So if protons are lighter than neutrons, the universe makes more of them. And it turns out that when you look at the temperature at about 1 second after the Big Bang, it turns out that you make, roughly speaking, I've just taken a random sample here of 16 particles, 12 of them, what have we got? 2, 4, 6. We've got 12 of them are protons and 4 of them are neutrons. Why does the universe decide to make more of the lighter particles? As far as we can tell, nature always favors the lower energy. Nature always tries to find the easy way out. This up here is a higher energy state than that down there. So if you let it go, it'll go from the high energy state to the low energy state. That is, okay, that's one particular tiny example, but generally speaking, it seems to be always true. If nature is given an option of being in a high energy or a low energy state, it will always prefer to be in a lower energy state. And lower energy corresponds to lower mass, because mass and energy have an exchange rate, if you like, of E equals mc squared. So because protons are slightly lighter, that means the universe will prefer to make more of them. Hence, the number of protons and the number of neutrons is not equal. Protons outnumber neutrons. We're now coming to about a few minutes, 2 or 3 minutes or so. Neutrons are unstable and change into protons. How do we know that? Because we can do it in the lab. We can take we can take a neutron rather, and it will decay into a proton. In other words, heavier particles tend to decay into lighter particles. We can watch neutrons do this. We know that a neutron takes about 15 minutes to change into a proton if left to its own devices. And so we believe that some of the neutrons in the early universe would have changed into protons. And so that set of 16, which was originally 12 plus 4, we think after a couple of minutes or so has now changed into, 14 and 2. There are now 14 protons for every 2 neutrons, simply because 2 of the blues have changed into 2 reds. And we believe that's the case because we can do the experiments in the lab, and we believe the early universe was no different from the lab that we have here on Earth now. After 2 or 3 minutes, the universe is of order 100 million Kelvin or so in temperature. It is now possible, it's now cold enough, remember the Russian doll, it's now cold enough not only for quarks to make protons and neutrons, it's actually cold enough for protons and neutrons to start to cling together. And what they choose to do is, given the option, and again, nature always takes the lowest energy state, given the option, 2 protons plus 2 neutrons makes a structure which we know is extremely stable. It's a low energy structure. In other words, if we allow 2 protons and 2 neutrons to get together, you end up in a lower energy state than if they were separate. And nature wants to be in a low energy state. Balls always roll downhill because that's the lowest energy state. So if we look at those 16 particles, if we know that 2 protons and 2 neutrons make a low energy structure, we call that structure an alpha particle, or we might call it the nucleus of a helium atom. You can see that all the neutrons in those 16 are used up, and we now have 12 bachelors, because we originally had 14 protons and 2 neutrons. 2 protons and 2 neutrons have got together to make a nucleus of helium, but we're left with 12 bachelors because they no longer have any neutrons to grab hold of. And that's what we end up with after about 3 minutes. After 3 minutes, the universe is too cold to change that. In other words, after 3 minutes, the relative abundance of hydrogen and helium, because separate protons are just the nucleus of a hydrogen atom, and this structure of 2 protons and 2 neutrons is just the structure of a helium nucleus. After 3 minutes, the universe is too cold to change it, and therefore the abundance of hydrogen helium is effectively set. In other words, what we should find is that by mass, the universe should be 3/4 hydrogen and 1/4 helium, if our understanding of the early universe is right. If the laws of physics then are the same as the laws of physics now, then the universe ought to have 3/4 hydrogen and 1/4 helium. When we actually look and see what's out there, what do we find? The universe is full of 3/4 hydrogen and 1/4 helium. If those numbers came out to be radically different, then that could not be right, and we must have got the physics wrong somewhere. So the fact that the Big Bang Theory makes essentially a prediction that the universe should be full but not 100% full of hydrogen is a good indication that the Big Bang Theory has some credit. Doesn't mean it's right, it just means it has not been proved wrong, and no one yet has come up with a better theory. So that's why we say the universe was born in 3 minutes, because all the action is now over. All the excitement is done. We've now created everything we need to make everything that's in the universe that we see, and it takes 3 minutes to do that. The next 377,000 years are very boring because nothing really happens for the next 377,000 years. 3 minutes of excitement, and then 377,000 years of not much in particular. The universe will continue to expand, it will continue to cool. Eventually, the universe cools to a particular temperature of 3,000 Kelvin. And the 377,000 years is the length of time we think it takes for the universe to cool to about 3,000 Kelvin. Why is 3,000 Kelvin relevant? Because if you take stuff, whether it be this glass of water or the table you're sitting at or the grass outside, if you heat things up enough, atoms fall to pieces. But below that temperature, atoms can form. In other words, once the universe has cooled to about 3,000 Kelvin, it looks like that's a battery. Do we have any mains here? We have some. Yes. Yep. It should last. I'm not sure if it's the TV that's doing it, but it should last for quite a while, so I'm not sure why it's complaining the battery's a bit low. So we're saying that at 3,000, once the universe has cooled to 3,000 Kelvin, the temperature is low enough for the atoms to form. I think I might have to drag this a little bit closer. So at 3,000 Kelvin, it is now possible for the nuclei that we've been talking about to actually hang on to their electrons. In other words, up till now, the universe has been too hot. Any attempt to bring a nucleus of an atom and the negatively charged electrons up to the atom, any attempt to make atoms, the universe was too hot and they would be ripped apart. But below about 3,000 Kelvin, it is possible to make atoms. So at this point, 377,000 years, this is the first point in the universe, the first time in the universe at which atoms existed. So instead of having a plasma, a mix of lots of charged particles, some of which are positive and some of which are negative, we now have a lot of neutral atoms, positive nucleus with negative electrons, the total charge on the atoms will be approximately nil. And this is the first point at which the universe becomes transparent, because we no longer have a plasma of positive and negative charges which will stop light moving through the universe. Because we now have atoms, the universe is transparent and light can quite happily travel through the universe. So that's why this particular point is important, 377,000 years, because it's the first time at which the universe becomes transparent. Up to that point, light was trapped in the sense it was like a pinball machine. It was continually rattling off all of the positive and negative charges that were inside the early universe. But from this point onwards, the light can fly unimpeded. And we can see that light today, the afterglow, if you like. 3,000 Kelvin, what do things look like when you heat them up to 3,000 Kelvin? You know that when you heat something up to about 1,000 degrees, they start to, if you take a block of tungsten or something, heat it up by a few hundred degrees, nothing much happens. Heat it up to 1,000 degrees, it starts to glow orangey. Heat it up to 2,000 degrees, it starts to glow white. So objects that are at a few thousand Kelvin will be white hot. So the universe was white hot when it suddenly turned transparent, and so there was a lot of visible light flying around the universe. And we now see it. But the wavelength that we see is now longer because the universe is now some 1,000 times bigger than it was at this particular point, 377,000 years after the Big Bang. If the white light, if the visible light with a wavelength about a micron or so is now expanded until it's 1,000 times bigger, then light that did have a wavelength of about a micron or so now has a wavelength 1,000 times longer. In other words, a millimeter. So the light is not visible light. The light that we see is the cosmic microwave background. We see it as microwave. That is the light that was released when the universe first turned transparent, when it was white hot. And we see, by looking in all directions, we've taken an all-sky map and basically wrapped it back into an ellipse here to get an idea of what the whole sky looks like. And it is not perfectly uniform. Remember, the golf ball had dimples in it. Well, the sky has got dimples in it for the same reason. The original golf ball produced dimples which gave rise to variations in density and temperature, which we can now see if we look at the cosmic microwave background. So the fact that this cosmic microwave background exists in the first place, and the fact that it has that particular variation of some hot spots and some cold spots, again lends credence to the idea that that's how the universe began in a Big Bang. Because if you disbelieve the Big Bang, then not only do you have trouble explaining why have we got this much hydrogen and this much helium, you have trouble explaining why we have a cosmic microwave background as well. So a lot of people will be studying the cosmic microwave background, the CMB, because it's not smooth, because it's got structure, because that structure is telling us about the early universe. The small variations, it's not so much the large variations that are in there, it's the small variations that we can see there. If you study that to enough precision, you can get information that constrains how the Big Bang must have happened. So that is why we've sent satellites up to try and measure the microwave background as accurately as possible. And if we just remind ourselves that the universe used to be the observable universe, everything in the observable universe used to be in something that size, although it takes some imagination, we can run simulations and say, let's follow the expansion of the universe from the very early days to the later days. Let's start with a universe which has some variations in it of density and temperature. In other words, let's start with a few dimples, and then run a simulation that lets gravity take effect to see what happens to a universe that has some small variations of density. Gravity works on matter, and therefore the most dense regions will collapse before other regions, and what we actually see in simulations is that the universe collapses into a structure which can be likened to a sort of web-like structure with lots of filaments and with voids where we get apparently not much going on. Where filaments intersect with each other, we seem to have some very high density regions, these white blobs here. These regions are where the galaxies, the clusters of galaxies, the superclusters of galaxies are going to form. And we can see that they're not randomly distributed, they follow particular structures. These filaments, the sort of things that we saw when we did the Sloan fly-through right at the start of the talk. So the fact that these simulations agree reasonably well with what we actually see in terms of the distribution of galaxies, again gives some credence to the fact that maybe we're applying the laws of physics correctly when we look at how we go from the early universe to the present day. If we look at what's going on in our neighborhood, here's the Milky Way in the center and a few galaxies in the local group, it doesn't look like the sort of structure we've just looked at because we're looking at too small a scale. If we go up to a larger scale, we see the local group in the center, and we see some of the clusters that are close to us, the Fornax cluster in the bottom left, a Leo group in the bottom right, a Virgo group in the top right there. So we're starting to see some of the clusters in our neighborhood, and we're starting to see the fact that these things, again, are not uniformly distributed. We seem to have a filament. Those clusters seem to be on a very rough line. And if we go out to larger scales still, we see again that we have a structure in which galaxies and clusters of galaxies appear to be ranged in filaments, and there appear to be some regions of space that don't seem to have many galaxies at all. The so-called Bouteille's void, for instance, appears to be bereft of galaxies. And again, the reasoning is what we've already looked at. If we start with a structure which is not uniform, then there will be some regions that collapse into dense areas of galaxies, and there will be some regions that appear to end up as voids, as indicated by the simulations. So again, the simulations which are based on our understanding of the laws of physics seem to bear some relationship to the actual arrangement of galaxies in our skies. On the largest of scales, the universe looks very foamy. This cosmic web, this is again a simulation, but it gives an idea of how uniform the universe is presumed to be on the largest of scales. Whereas if we actually zoom in and look at a particular area and look at a particular set of filaments that seem to be crossing, we seem to say, okay, that seems to be where the galaxies are actually forming. If we zoom in, if we have a minute or two, let's just zoom in to the overall structure. This particular simulation was carried out about 20 or so years ago, which is why it's called the Millennium Simulation. A simulation taking an awful long time on a supercomputer, tried to calculate what the overall structure of the universe looked like. And here you can see that we're zooming into a particular region to see that although it's uniformly foamy on a large scale, as we zoom in, we see particular regions which are bereft of galaxies, these voids. And if we look at where the filaments cross, we see that's where galaxies appear to be being made. It is thought that matter effectively streams down the filaments, like matter going down a plug hole, and starts to collect in these regions, which is where the galaxies actually form. And when we finished zooming in, we're down to the point of looking virtually at individual galaxies. We can see that we're not worried too much about the structure, but we can see that's where galaxies form. We zoom out, we see the filaments down which the matter has produced those galaxies. Then we see some of the voids, and as we pull out, we start to lose the detail, and then we get the overall structure of the universe, which appears to be this web or foamy structure, which is believed to be the structure on the largest of scales. But of course, we haven't mapped out the entire universe, the entire observable universe, to confirm that just yet. So now that we have hydrogen atoms, which only takes 3 minutes, now that we have hydrogen atoms, effectively we can say, well, the rest is easy. If you start with a shed load of hydrogen, then the rest is just turning the handle. We can now understand galaxies. We can now understand stars. We can understand planets. We can understand trees and mountains and snowflakes and rainbows and cats and, okay, probably not cats. I don't think anybody understands cats. But we can basically, if we start with enough hydrogen, we can now say, right, now we can understand how all the other elements in the periodic table come about, and we can understand why the universe looks the way it does. So to put it on a graphical timeline as a sort of graphical summary, a ridiculous timeline that starts at 10 to the minus 35 seconds on the left, where the cosmic golf ball starts. The golf ball expands, energy and matter continually swapping backwards and forwards. We start with a quark soup, which is actually a soup of quarks, and electrons and loads of other particles as well. If you wait long enough, the quarks can come together to form protons and neutrons. If you wait a little bit longer, the protons and neutrons will get together and make structures such as helium nuclei. All of the protons that are left over are now what we call hydrogen, because a hydrogen atom is simply a single proton with a single electron. Eventually those electrons team up with the atoms, at which point the universe becomes transparent and the light is released to form the cosmic microwave background. That happens in a fraction of a million years, and after that, which I haven't said anything explicitly about, the so-called dark ages, because it takes a little while before you can make stars. Yes, you have to start with a lot of hydrogen, but it takes a while for the first stars to be born and live and die. And that happened in the very early part of the universe, early in the sense of after the cosmic microwave background was formed, but before, let's say, the first billion years. In other words, as seen from now, where we look at galaxies close to us, if we wanted to go back and look at the very early star formation or the very earliest galaxies, we need to go back most of the 13.8 billion years in order to see those early galaxies form. Hubble is doing its best with the Hubble Deep Field, trying to look as deep as possible, as far back in time as possible. The Hubble has managed to go back about 13 billion years out of the 13.8 billion years of the universe's existence. It is hoped that the James Webb will be able to go back perhaps 13.5 billion years back in time of the 13.8. So it's still not going back to zero. Nothing in terms of light can go back further than the cosmic microwave background. So we're always going to have that limit of the first fraction of a million years, but we've still got a way to go to see the earliest stars and the earliest galaxies being born. So the jigsaw is by no means complete. There are still some problems. There are still some questions that remain unanswered. I've been talking about how can we possibly understand how everything that we can see in the observable universe could have started from something like this and then developed in the way I've described. But we still don't understand why matter won over antimatter. We know it did because we're here. It must have done. But we don't know what actually prompted the asymmetry. We can measure asymmetry in the lab. We can measure matter and antimatter asymmetry in the laboratory using the Large Hadron Collider, and we know the asymmetry exists. We don't understand what caused it in the first place. We also don't know what dark matter is. I've been talking about what we can see, what we can actually observe, but of course dark matter, we've had to infer the existence of dark matter from its effect on what we can see. So something is out there causing the galaxies to rotate at what you might describe as the wrong speeds. And also there's this other elephant in the room, dark energy, which is causing the universe to accelerate its expansion. We might think that as the universe expands and cools, gravity will slow it down, but it appears not to be slowing down, it appears to be speeding up, and that was a bit of a surprise when it was measured a couple of decades ago. So there are some serious problems with what we understand about the universe. We think we've got the basics right, but these three questions still need answering. The talk is entitled The Beginning of Everything, but I've tried to make it clear by everything, I mean everything that we can see, everything within the observable universe. But everything that we can see, all of the gas, all of the stars, all of the galaxies that we see in the observable universe, all of the stuff we can account for, is only about 4% of what we appear to think is out there. The other 96% is still a bit of a mystery. But that, as they say, is another story. Thank you all for listening.